Hello everyone, my name is Yao Bing, who is a PhD candidate of University of Minnesota. Today I'm going to present my paper, Accelerated Deduplication by Prefetching Backup Content Correlated Fingerprints, PBCCF. Here is the outline of my presentation. First, I will introduce the background of the data deduplication. The data deduplication has widely implemented in large-scale storage systems, in particular in the backup system. The unique data is saved in the storage, while the duplicate data is only required to save its index. The backup administrator typically creates multiple policies based on the different backup types and different service levels. A single policy protects multiple clients, and the clients in a policy share the same backup frequency. Due to the different characteristics of the full and incremental, the incremental backup generally have much lower redundancy. Our paper only consists the full backup. The duplicates of the backup string will be identified and eliminated, and the unique data segment are saved into the containers. Due to the dedupe, the container may be shared by several backups. The client policy system we focus on is shown in the slide. In this system, the dedupe is distributed to client side by prefetching effective fingerprints from the server side, which significantly reduces the network traffic and the latency issue. Also, the dedupe process has a good scalability because the computing resources required only provided by the clients themselves. For this system, it is hardly possible to adopt full indexing that prefetches all the fingerprints to memory for dedupe. Due to limited memory, partial indexing is used to maintain a small portion of the fingerprint for dedupe. The research problem is how to efficiently determine the correlated fingerprints to be prefetched to the memory for maintaining the deduplication rate. For the existing clients, the backup has similarity to the previous one in the same client, so we can just need to prefetch the latest backups to the memory. But there was no efficient approach to do the dedupe for the initial backup from the newly created clients. Because for the initial backup from the newly created clients, there is no historical backups for reference to do the dedupe. In order to do the effective and efficient dedupe for this case from the newly created clients, we observe the backup content correlation among the backups from different clients in the real backup system. We found that the dedupe rate could be significantly improved if prefetching a right backup from the other clients. For example, if prefetching the backup from the client 175 to dedupe the initial backup from the client 371, the dedupe rate is only 3.2. However, the dedupe rate can be improved to the 47.9 if prefetching the backup from the client 404. In other words, the duplicates exist in different clients. The reasons are various. Container usage is one of the key metrics to design the PBCCF. The container usage data includes the container ID and the size of the data content saved in the container for that backup, which is shown in the 2D plot. The data points in the plot shows high spatial locality in terms of the containers. As we can see, the data points are not randomly distributed, but divided into the several groups. When we plot the container usage of the backups, we found the backup prefetch achieves the best dedupe rate, has the most similar container usage. Hence, one of the key points we generalize from the real backup system. The backup similarity can be approximated by the container usage similarity. If we're using this approximation, the computing overhead will be greatly reduced by calculating the backup similarity using the container usage data instead of using the fingerprints. PBCCF are proposed to optimize the dedupe rates of the initial backups from the newly created class by localize the most similar backup and determine the highly correlated fingerprints. Now, let me introduce the design of the PBCCF. In the server side, we maintain a fingerprint catalog to hold the fingerprints of all clients' latest backup. Their container usage data are generalized and input into the Container Usage Pattern Mining Component, CUPM. The CUPM has a combination of the learning algorithms to discover their patterns and learn their features. This process is run offline that will not impact on the DDU process. Additionally, it requires very little overhead. Based on our testing, applying the CUPM on the 4.5 terabyte backup data only requires 3 minutes and 3 megabyte storage. In the server side, a small local window of the initial backup from the newly created client is indexed from the Fingerprints catalog for approximately obtaining its container usage data. The similar CUPM approach to get its patterns. An effective approach is designed to measure the distance between the processing backup and the historical backup. The backups with the shortest distance will be considered as the candidate backups. In these algorithms, there are 2 parameters here. What's the size of the lookup window is good enough to approximate the container usage of the processing backup. And the second, we want to see the performance behavior. It varies based on the different prefetching number. And now we define the PBCCF1. It will prefetch a single backup from the candidates to dedupe for testing the ability of the PBCCF localizing the best backup. And we focus on 5 policies and 55 clients backup data collected from the real backup system. If the worst backup is prefetched for the DDU rate is as low as 10.6. But if the best one is prefetched, the DDU rate can reach 30%. From the results, we can see the DDU rate of different prefetching number are increased at the beginning, then saturated at 5% lookup window. Hence, only 5% lookup window in our dataset is sufficient for the CUPM to approximate the container usage of the process backup. The prefetching number was incremented to see the performance of the PBCCF to identify a good base backup. We can see the DDU rate has 4% improvement when increasing the prefetching number from 1 backup to 2 backup. Then it is saturated at 26.2 when increasing the prefetching number to 4. The gap to the optimal deduplication rate is less than 4%, and then we can still claim that the PBCCF succeed in improving the DDU rate for the initial backup from the newly created client. However, not all the fingerprints of the candidates can contribute to the DDU process. To improve the effectiveness of the fingerprint prefetching, the number of each container shared by the candidate backups are counted as an example in the left figure. The fingerprints marked in red, whose container has high number of the counts, are prefetched to the memory for dedupe. We evaluate of the performance on dedupe by varying different memory size from 30 MB to 120 MB for prefetching, which is shown in the right figure. From the results, we can see the PBCCF has only 3.7% less DDU rate when using only 120 MB compared to prefetching all the fingerprints that requires terabyte memory. There were 2 generic prefetching algorithms based on the sampling approach for client policy deduplication system. Progress sampling is an extending version of the sparse indexing, and the progress sampling will be the related where we want to do the comparison. Now, let's do the comparison of the memory usage to maintain the DDU rates between different prefetching approaches. After the optimization, we can see the PBCCF2 saves at least 4 times memory while maintaining the same DDU rate as the PBCCF1. And without considering the backup content correlation, the progress sampling requires at least 40 times memory to maintain the deduplication rate, as shown in the table. Conclusion: the CUPM approach only uses a lightweight machine learning algorithms, and the input of the CUPM is just the high-level metadata, and the additional overhead of the implementing the PBCCF is negligible compared to the full backup process. In our project, I got a lot of help from my manager, mentors, performance testing team in Veritas. Okay, that's all. Thank you.